Welcome back, everybody. This is Donald with the VRF Tech Talk podcast, joined again by Roman Ball. Today is going to be a loose one. We're we're going to talk about failure modes of compressors and what Roman and I have commonly seen in our time working on this VRF stuff. Some tips and tricks on how to avoid it and what some teardowns look like. So first and foremost, we got it up on the big screen, a torn down compressor. So I'll let Roman take it away. Maybe give us a little background on what happened to that compressor, and then we'll talk about it.
Yeah, so today we want to go over common components. So it's so easy to sit here and talk from our very fancy big microphones in front of our faces and just say, "Oh, compressors don't die; they're murdered." That's the catchphrase. Maybe I will eventually trademark that. I don't know who started that, but we could definitely trademark it. And it's one of those things where when we get into diagnosing failed compressors, there are a lot of articles out there. There's a lot of stuff that I've made videos on that people have written tech tips about, and very knowledgeable people like Ty Brenneman, one of the bigger ones that comes to mind there, about megging compressors and finding out the root cause of the failure and all that stuff like that. But we never really talk about the parts and pieces that go into compressors and why these little tiny things that we talk about actually matter. And so I've got probably about 100 photos here of a number of compressor failures that I have cut open, that I know of other people who have cut open using a compressor cutter. There's a couple ways to cut open compressors, guys. There's the very difficult way of cutting it with a manual cutter. Who's the person that makes that, Donald? Do you know this off your head? Is it Snapdragon or something like that? I think it sounds familiar. There's a actual large compressor cutter that you can buy. It's like a big set of copper cutters. It's two wheels and a big blade. And so you can manually sit there and rotate it over and over and over again. And I've actually done it once before.
I didn't even know it existed.
I will never do it again.
I'm
sure I have a picture of it here that I could pull up for us. But with that being said, it's one of those things where there's that method, and that method is very labor intensive. You probably get lucky to get through one compressor in that day. The other method is using an angle grinder. Well, the problem with angle grinders are that anything that you use to cut open a casing like that, it's very violent. It's very it's just messy. And so what happens is you get cross contamination in the actual compressor, and that cross contamination then kind of messes up what you're trying to do in the first place. And that's find the root cause failure of that compressor. And so it does get you a closer look at the components inside. It lets you get familiar with what's inside, and maybe you find a screw. Maybe you're lucky. Maybe you're one of those people that's actually found a screw. I've yet to see it, but I have been told that it exists somewhere, I suppose. And so with that being said, the last method, the third method here, is the compressor cutter that you can have built. There's a steel cutter made by Rigid that's designed to cut steel pipe. That steel cutter, it will actually allow you to, rotate it using a hydraulic press, and it takes about maybe, 30 seconds to cut that compressor open. Here is the picture of the actual compressor cutter. Here you go. There's the manual one, right?
Oh,
so
wow.
It's got a big old hand lever on it. It's a freaking mess. And if you don't line up the cut just right, it's a pain, but it's basically snaps around it, and then you tighten up the handle. It's two blades. And it is very, very labor intensive. So it's a big arm workout for sure. But so when we're cutting open compressors, angle grinders, manual cutters, or hydraulic presses, obviously the one I prefer is hydraulic presses just because you can get through it pretty quickly. But the important thing to remember here is that with that hydraulic press or any kind of manual press, we get to use anything we find inside that compressor towards the failure analysis. That's the big thing. If we have zero contamination from the cutting process, then anything we find inside this compressor is a contributing part to that failure, right? Remember that refrigerant that's flowing through a VRF system is flowing everywhere. It flows through strainers, expansion valves, solenoids, liquid receiver, accumulators, screens, filters, and it makes its way all the way back to the compressor. And so if you know that all refrigerant goes through the actual compressor, then we know that whatever we find in here can be contributed to the failure or at least the health of the system. And that's the important thing to remember here. And so easily looking at this picture here being cut open, this photo actually comes from a good friend of ours out in Boston. And this is a VRV3 compressor that he cut open. And you can see here, actually, it might even be VRV3. No, that's actually an X compressor. That's a pump on the bottom. Either way, here you can see we have magnets at the base. So why do we have magnets at the base? Well, that's because the scroll plates on these compressors, for Daikin at least, are made of cast iron, right? And called cast because it's a cast part. That's how they make it. It's the smelting process of actually manufacturing the scrolls themselves and polishing them and going through that process. When those scrolls become unlubricated, whether it's liquid refrigerant in a small amount coming back and diluting the oil on the scroll plates, whether it's large amounts of liquid refrigerant coming back and washing the scroll plates and pulling the oil out of the compressor, or and running unlubricated, or a lack of refrigerant coming back to the compressor, which again, oil gets trapped in the system downstream, doesn't come back to the compressor. It mills down those scroll plates to the point where it looks like this. It looks like you have big, fat, metallic donuts at the bottom. And these are actually metal rings that are designed to catch some contaminants in the system. But the problem is that that's the magnetic portion. There's a whole other spectrum of contaminants that can get into compressors that are non-magnetic, that we're going to talk about here and look at, that can cause problems as well. But that's the basis of what we see here. Obviously, you see the compressor shell at the top. The next thing here on this list is the base of the compressor is the oil pump turned upside down that goes in the base. The bottom left hand is actually the inlet, the suction pipe. Here, this is the top of the compressor. This is where all your suction gas comes into the actual top of the compressor. These are high pressure shell compressors. So discharge gas goes up the top, comes down to the shell. And then again, that the right hand bottom side is the base of the compressor. This is where the oil lives. This is usually full of oil, supposed to be full of oil, at the base. And you can kind of see some murky discoloration in the middle that, it just pools up at the bottom. So,
You know what's not supposed to be there?
what's that?
Metal.
Yes. No, so again, these magnets aren't here by design in regards to being able to catch a bunch of crap in the system. These are used as a last ditch method to protect the compressor. It's no different than a screen in a system. The screen in the system is 100 mesh in most VRF systems.
50
It's
or 100,
designed,
yeah.
yeah, it's designed to catch large contaminants from flowing through the system. Now, an ideal perfect world, brazing with nitrogen, clean system, proper evacuation, proper charging with clean refrigerant. You don't have to worry about any of this stuff. But if you let a system go, you don't service it properly, you don't charge it properly. I mean, there's a whole list of things that could cause this specifically. This is the end result. You get this milling of the scroll plates that results in shavings in the base where it overloads the magnets. And then what happens after that? I've got a nice little picture here at the top of what happens once it overloads the donuts. And this is actually a really
So,
nasty.
back to filters, like the screens and the things that we're talking about that are in these systems, right? So, sorry to interrupt, but I think it's good
Oh,
to
yeah.
talk about, like, in a VRF system, you're going to have 50 to 100 mesh screens all over the system, right? You're going to have them in your fan coils, you're going to have them in your branch selectors, you're going to have them in the condensing units. But let's think about what 50 mesh means, right? 50 micron or 50 mesh, right? The particle size of the stuff that gets through there. Yeah, click on that picture. Look how big that opening is, right?
Yep.
50 microns or 50 mesh, 50 micron or 50 mesh is equivalent to like a quarter of a millimeter, right?
So, and the
Right.
way I like to describe it too, if you think about 100 mesh to 50 mesh, um, a human hair, the diameter of a human hair is 75 microns. So that kind of puts it into perspective for you. Now you say, well, that's really, 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 really small. Well, sure, right? But if hair can get through a 100 mesh filter, and it could probably get through a 50 mesh if it's small enough.
Sure. So 50 mesh is 297 microns.
Okay, gotcha.
297. Right? That's a quarter of a millimeter for
Yeah.
people that want to know millimeters, right? So I'm a nerd. I carry this tool everywhere. A millimeter. Right? That is a millimeter.
Yeah.
It's huge.
You can see it. Yeah, it's sand, right?
Right? So these screens are not there to save you because you didn't do a good job with purging, or you got copper shavings in your system, or you were open up to dirt and you got rocks in there. Stuff will get past these screens. That is a 100% guarantee until, what's happening on the top of that picture. Oh, this is a good one. Until that happens, right? Until you get that thing so plugged full of stuff that not even the oil flows through it anymore.
Yeah.
Right? Not even a fluid can get through that.
And so it's the whole chicken and egg. And I've had this conversation many, 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 many times that people want to find out what started this, right? And everybody is looking for someone to blame, and we're not here to play the blame game. I'm here to find out what killed the compressor and also what are the other mitigating factors that contributed to its death. Now, I can't sometimes with these symptoms and things that we find in the system, especially like this, there's this, delineation where I have to figure out, okay, well, I found this, I found this, I found this, I found that. Putting them in a specific order to figure out which one came first is almost impossible in some of these cases.
Right.
So it still doesn't really matter. What's the solution for this?
It's right. All we really want to find is the root cause so that it doesn't happen again.
Correct. And so when you say, and there's a whole mixture of stuff in this one, between chunks and pieces and particles, copper shavings here in the center, sludge, there's a ton of stuff we can unpack here. This is the one that I have that I pulled the magnets out. Look at that oil. That's black. That is some black oil right there.
Right, well, how do you get black oil, right? So what happens to the oil? I think we touched on that in that episode that we did with Ty, and you guys have done some further experimentation on the oil. Like what causes the oil to turn black other than obvious contaminants?
So what causes oil to turn black is also a process. Basically, it's overheating, right? So when we talk about PVE oil breaks down, starts carbonizing at 247, and carbonization is basically, we're messing with the molecular chains of these polymers to where they're binding in different ways and creating something larger than themselves. And this black, it's a combination of stuff. And we can sit here and and this is the thing that I have a problem with sometimes is we can sit here and we can look at this and we can go, let's determine what this is. But until you actually take this oil and send it to a company in a lab that can actually go through and analyze this oil to tell you exactly what it is, we are still kind of guessing in a way, right? Black oil, we can say from experience, it's usually overheated compressors combined with contamination within the system and probably a really nasty, dirty burnout of the actual windings themselves, whether the windings or whether it be the plug on the windings on the shell casing, it's burnout. And that's what we see here. Now, how acidic is it? How many particles is in it? Is there copper shavings? Is there iron shavings? Is there other contaminants that are not supposed to be present in the system, like sand? We wouldn't know that without actually taking a sample of this and having it analyzed either under a microscope or having a spectral analysis done or having some kind of metallurgy done on it to determine what it is. We can see this and say, yes, I know from this picture 100% you need cleanup, right? This needs to be cleaned up in the system. If this is compressor 1 of 6, what do the other 5 look like? And they probably look pretty close to this. And if they don't look close to this, how much of this is in the system? How much of this left the compressor and is throughout the system? Because one that I think that a lot of people check is the strainer right above the discharge check. So out of the discharge line of most VRF systems, it goes into a refrigerant oil separator, and it's fairly decent at separating oil. That's the actual strainer that we see here that separates out the bottom, that oil that comes back to the suction line. But out of the top of that oil separator is a check valve and actually a metal screen. It's a pretty big metal screen. And I tell people that again, with all the refrigerant passing through one compressor, there is also refrigerant passing through that strainer and filter too. All refrigerant flows through that at some point out of the compressor. And so if you really want to, if you see something slammed like this one, I'm really curious to see what people might find if they pulled out the discharge, strainer that's right above the check. Because how much stuff got past that check? How much stuff got caught in that strainer? I mean, you might be surprised to find out what's in there too. So, but how do we check strainers, right? What's the process of determining this in the first place? If I'm changing out a compressor and I didn't get a chance to check the strainer before the compressor died, then it's probably just a good idea to go ahead and cut it out and change it out anyways. But if a system is running, the procedure for checking that strainer is measuring temperature differential.
Right. Take a delta.
That's it, right? Temperature correlates to pressure. And so if we have large temperatures changes across something that is not supposed to be restricted, then we know that there's a pressure drop there. There's a pressure restriction in that line. And so that's something that should be investigated and changed out. And in a perfect world, there would be a 0 temperature difference across this. But I think, maybe 3-5 degrees, somewhere around there. Any way you climb up in that number, the more uncomfortable I get with you leaving it in the system.
Right.
It's one of those things where when we talk about VRF, variable refrigerant flow or variable refrigerant volume, what hinders flow? What hinders the volume of refrigerant? Well, restrictions in the system. This is an obvious one. And this is the dirtiest one because this is basically an oil filter. I mean, I don't know, when last time someone changed their oil on their vehicle themselves, But I mean, if you've seen the oil that comes out of some vehicles after 5,000, 6,000, 7,000 miles, I mean, you were in the auto industry, right, Donald?
Yeah, I was say like I was gonna make that analog, the magnets in the bottom of the sump of those compressors, right? Like we put a magnetic drain plug inside of a car, as it's getting older in life, and then we take it out and we got particles stuck to that plug, and we know that, hey, this thing is going through bearings. There's probably an issue here. It hasn't manifested completely yet, but it will. And that's the one thing we don't want to see is sparkly oil. Like it's the same concept here is we don't want to see sparkly oil.
We don't. It's that glitter that you see in the system, because now you have to ask the question, well, where did it come from?
Well, that's gold. I was panning for that. That's gold.
I should have had them remove that and sample it, send it to me so I can analyze it. But that's the thing, is that this is in the base of the compressor because that's where all the oil goes. And you have to remember, when we have refrigerant oil separators, people are going to argue, as they do, and that's okay. I like a passionate debate just like anybody else. They're going to argue, well, the refrigerant oil separator separates all the oil out. Well, we forget that the oil separators that we use on VRF are wildly different than refrigeration. We are using that centrifugal force, right, inside the actual oil separator. And so the slower the refrigerant moves through that oil separator, the less efficient it becomes at removing the oil.
Right.
And so at low RPS, how much oil are we getting back really? And we're not. And that's kind of why oil return mode goes more frequent. The lower the speed is, the longer it stays at low speed. Right. And so,
that's a good point that I think is often overlooked too, is if your building is living in a semi-loaded state and it's just barely putting by, right? Like you may never see an issue because it's hitting oil return, and then all of a sudden, boom, you have a failed compressor.
Yeah.
Well, this might be why.
Yeah, well, and that's the thing too. So because it becomes less efficient at the lower speeds that these systems run at, right, you have to remember going into oil return, those things all kind of stack up and build up. And so, when we look at systems like this and you think about, okay, well, let's assume the charge is perfect. Let's assume that the lines are the right diameter and size. Let's assume that they braze with nitrogen whenever they install the system, and there isn't any sand or rags or screws or someone's screwdriver, car keys in the lines. And we run this system. There are still chances where, you get a leak on the system and the refrigerant charge, right, less and less and less and less, and you get more oil pooling in the system. Or let's say that the system was unbalanced when it was designed, and you get one random fan coil they moved and put on a different port that's now 230 feet away from the BS box, and it breaks that 160 rule. Is it 160 or 130? Always miss both.
131.3.
Oh, see, look at you.
And so, at least I don't know the other manufacturers.
Well, everybody's different, but here's the thing: is the balance. So let's go to the figure of the application, right? So we move the unit. Now it's unbalanced because that unit is way far away. And when the unit goes into oil return mode, it starts sending liquid refrigerant through all the indoor units. It stacks as much liquid refrigerant, creates as much liquid refrigerant as possible in the outdoor unit. Compressors ramp up to high speed. It runs. It floods the indoor units with liquid refrigerant to scrub the oil out, because liquid refrigerant grabs oil pretty well, actually, I'm going to find out. Brings it back to the outdoor unit on the suction line and turns off oil return mode. Once that suction line sees that liquid refrigerant coming back on the suction line, it says, hey, I've got liquid. So it left the unit, it went around the sun, and it came back to me. And now that it's here, turn off oil return mode. The problem is with that imbalance is that fan coil that's furthest away starts to pool oil because it doesn't get all that liquid refrigerant that it should have gotten with all the other units. And so then it pools and it pools and it pools, and you get low oil quantity. Over time, low oil quantity leads to what's the top of the scroll, right? What's the top of the compressor? What's the highest point away from where the oil is in the compressor? And that's the scroll plates. And so what happens to those scroll plates when you start losing that total quantity of oil? You get this. And this is that paste that we see. Where'd that paste come from? The cast iron. It comes from milling down scroll plates at the top, right? This is the first place to become unlubricated when you get low on oil in a compressor. And what happens is that when it runs like this, it creates high discharge superheat, abnormally high discharge superheat, because now with unlubricated operation in the scroll plates, that compressor starts generating what? It starts generating extra friction that the refrigerant can't handle, and it overloads that refrigerant cooling effect that we're dependent upon to keep the motor cool. Right. Well, and so now you get elevated discharge superheat in the compressor. Well, the suction superheat's great though, but that doesn't matter. And the charge is great. that also doesn't matter. You broke the piping rule and we lost 16 ounces in an FXMQ 48 that's downstream. And so that compounds over time and over time and over time. You lose more oil and you become more unlubricated. And so what happens? Well, those shavings go down to the base of the compressor and they start to load the magnets. And as they load the magnets hold as much as they possibly can like this until they can't hold anymore. And then what happens? It starts to swirl around in the oil at the base. And where does it go? Well, it goes up the center shaft.
Back up one step, even before we get back to that, right? So once we have a loss of oil in that compressor, you touched on it briefly, but I think one of the secondary or tertiary even failure causes could be, right, once we're heating that scroll plate up because we've lost friction, that heat has to go somewhere, right? And what is that compressor made out of? It's just a big chunk of metal that's all touching each other. So where is that heat going to go? It's going to go right back into the oil. What's going to happen to the oil? It's going to overheat. What's happening is when you overheat the oil, you lose lubricity again, right? And then you compound, right? So as we're losing oil, we're heating the oil we do have, we're losing the lubricity of it, and we're just continuing to kill this compressor because of a simple oil return issue.
And that's the thing. And that was a small application problem, right? And this is what we're describing is happening over 3 years. This is happening over 4 years. It's happening over 5 years, if they're lucky. And to Donald's point, it's a cascade effect. This started with a poor application that nobody caught when they broke the rules on site and didn't actually build a VRV Express or even, looked at it to say, hey, what are our application guidelines that we need to follow? We have to follow because of this. And so we mill, right? We overheat our oil. Our compressor runs hot. Our windings run hot. We fill that bottom sump from all these little tiny hair shavings that you see. I mean, you can see them right here, shaved off the actual surface, hanging on by a thread. And so they overload the magnets. And what happens when they overload the magnets? Well, then we start getting into the territory of the base of the sump. High pressure shell compressors rely on pressure differential to push. That pressure pushes down on the oil at the base of the compressor to push it up the center shaft up to the scroll plates at the top. Well, what happens when the magnets get overloaded? Well, they start to clog and plug where the oil goes in the center shaft. And once the center shaft gets plugged completely, then you run into the issue where now everything stops becoming lubricated. Not just the scroll plates, not just the orbital, not just the fixed. We're talking about the upper sleeve bearings. We're talking about the old ham coupling. We're talking about the lower sleeve bearings. It all starts to overheat. I mean, just look at this. This is the center shaft on a VRV3 system. Look at these giant turds. You'll never hear me say that on the podcast again, probably. But look at this. This is giant metal paste from scroll plates, and there's copper flakes in there. You can kind of see it right on the surface there with the reflections that it has and kind of that gold pattern. It's sludge. This entire center shaft was plugged with all of this, compounded and pressed against each other to the point where I knocked it all out. And now you can see down the center shaft. I mean, and it's a pretty big, you can see my finger here. That's got to be what, 1/4 of an inch opening?
I'd say it's probably 3/8 of an inch. Yeah.
Yeah. Something close to that. But look how much was compacted in the bottom. Now this is the same compressor that you saw there. These are the magnets. Look at those magnets. Here. Okay. So you're like, okay, well that looks messy. Sure. But what does it actually look like compared to a clean magnet? This is it, right?
It's like doubled in size.
It's a donut. And look at all the things that get trapped in there. So a lot of these things aren't metallic. The things that you see that are metallic kind of stick out like this to follow the magnetic fields that surround the magnet. But some of this stuff just gets stuck because it's sludge, and it has nowhere else to go. And this is what happens. And then, okay, so now we're completely unlubricated because it's completely compacted. Where are we going next in this compressor? So we talked about the scroll plates. We're going to go under that scroll. This is under the orbital scroll. Under the orbital scroll, you'll see here, this is a sleeve bearing. This top, well, I say top part. This is the base of the orbital scroll. It's the old ham coupling down here. This sits perfectly on the top of the rotor. Where is that picture? Here we go. Sits right here. So the old ham coupling slides right on top of this rotor. And these two, it's like a sleeve bearing. And so it's designed to be lubricated. Where does it get lubricated at? I've got a picture of that, where that hole is. Here we go. It gets lubricated here. It's got small openings that are designed to push oil into those sleeve bearings so that when they spin on top of each other with those low clearances, they don't overheat. And now that they're not getting lubricated anymore, they get super crazy hot. And then what starts to happen? Well, they start to warp. I mean, what happens to metal when it gets hot? It,
It gets
you know,
pliable.
it gets super pliable, and to the point where it gets so freaking hot that now it's starting to shape into, a parallelogram or an octagon, right? We get these compressors that wobble whenever you turn them on. Someone was talking to me the other day about,
Ooh, the shaking compressor.
yeah, someone was talking to me about the ruptured capillary tubes that we get with your
that's
three.
your compressor has lost oil, and now it is a cause of leak, but it is not the cause of failure.
No, it's not the cause of failure. You get this sleeve that gets worn out and wobbled out, and once that one starts to go, then you start to lose the lower one, and the lower one looks like this. And so you can see the temperature discoloration because of the colors, that rainbow effect that you get, is a clear sign of wear, of overheat on that bearing, to the point where you'll find that some of these, and I thought I had a good picture in here, they get wallered out to the point where they actually lose their circular, design. They actually get a flat spot, and that's where that shake gets when it hits that side. It wobbles extremely difficult. I mean, look at this. This is like a copper paste.
I mean, to another analogy, right, for you automotive guys, right? That lubrication hole in the shaft there that fits on the bottom of yeah.
Rotor, yep.
Right. Think of it as the oil squirters for your pistons, right? And what we're trying to do there is to keep them lubricated so that the sides of our walls are lubricated. Our cylinder walls are lubricated, right? If it's not lubricated, what's going to happen? Well, you probably drive a Subaru, and you're going to get some rod knock, right? Eventually, you're going to get knock.
Yeah, and then what happens after that, right?
And then you sell your Subaru because it's a piece of crap.
But in this
True story.
aspect, yeah, when your compressor starts to separate capillary tubes from vibration, it's because of this.
Right.
Because it looks like this. This is the worn top part of the actual rotor of this compressor. This is the bottom part of that rotor that's also contaminated. Right below here is that plug that we talked about that sits in the oil itself. This is technically supposed to be submerged in oil. You can see all the copper shavings that are in there as well. And again, all these things play a factor. I mean, you can see how small these tolerances are. Let's look at something cool. This is the let me see here if I can find it. I got all these out of order, but that's okay. This is the suction inlet, right? So at the top of the compressor, there is a little disc on a spring. That disc on a spring is like a suction plate that's designed to
like a reed, not a reed valve, but kind of.
There it is, right there. It looks like that. And so when the compressor turns off, it floats to the top, and it kind of makes a seal on the opening of the compressor for the suction line to kind of prevent mitigation, if you will. When the compressor turns on and it starts to create suction, it pulls this down. Well, what collides with this plate? Everything in the system collides with this plate before it goes into, it's a 90-degree turn. There's no turning vanes in here. It's a 90-degree turn into the actual fixed scroll plate or the orbital scroll plate. These are both together in this spot. And this is, again, look at all this contamination that is just slapped up against the surface of this little tiny disc over time. This paints the story of how much contamination is actually in this system. I mean, I'd even venture to say maybe that's rust. We could look at this and we could say, well, it's this or it's that or it's this until we scrape it off. I mean, for all we know, that's sludge, that's acid that's eaten away and done some copper plating in the system. And here's a better picture of it with the surface. I mean, look at all those little tiny pieces of metal. And it does look like rust, kind of, doesn't it? And so this tells the picture. This tells a story. This is the story of what went through this compressor in its lifetime. Whether this is a year, this is 10 years. I see some copper flakes. I see maybe some solder droplets and pieces. You never know what you're going to find. But this is not good. Like, this is a really bad sign for a compressor like this. So it's one of those things where, you don't think about it. And if you never torn a compressor apart, you wouldn't know it. But all these things, they contribute to each other. They add to why it matters,
right?
Why it's so important. Why is it so important? And we were talking about this earlier about, things like brazing without nitrogen, right? What are the causes? What does that look like? And we're taking forever to, it's me. I'm sorry. We're taking forever to get this oil video done that I did with Ty, where we cooked compressor oil. We put compressor oil in the base of compressors. We made the podcast about it when we were doing it. And we found that when you cook oil, you can actually create carbon in such a short amount of time. It's kind of crazy. Somewhere close to 300 degrees, which I get why we have compressor step downs at 235, 240,
right. But realistically, that's probably already too late, right?
It is.
As we talked about in that podcast with Ty, is like, if the sensor that is telling us that the discharge temperature is 225 degrees is reading 225 degrees, that compressor is probably reading closer to 250.
Yeah, the sensor of the actual compressor itself is already way higher than what you're seeing on the discharge line. Because remember that the hottest part is going to be at that center core of compression in that motor, or any place that might be unlubricated at that point.
Right.
And so when we talk about, let's say, like contaminants like brazing without nitrogen, well, how detrimental is it? How many times is it actually going to kill compressors? Well, it may not be the main thing that stops a compressor from running, but it is definitely a contributing factor. And we found that out when we did the tests on brazing without nitrogen. We brazed, we had actually a bunch of pieces left over from brazing class that I taught, which is on HVAC School YouTube. We went through and I cut them open as we do. And we basically soaked them in oil. We did mineral oil, PVE oil, POE oil, and we did RX11 flush. And we found that the RX11 flush didn't clean the copper, didn't actually remove any of the, cupric oxide that built up on the surface. The mineral oil didn't do it either. It didn't clean it at all. It actually came out the cleanest. POE oil ended up stripping the copper clean to the point where the oil that came off of it and that was left over was just black. And then the last one, which is PVE oil, we found actually stripped the copper clean, not as clean as the POE, but it actually probably got about 80% of the cupric oxide off the copper. And so when you braze without nitrogen and it runs long enough, it doesn't happen right away. When it runs long enough and the oil circulates through the system, you'll find that it actually strips the copper clean. And where does all that go? It goes back to your compressor in the oil. And that's where it lives for the rest of its life. Like that's where it's going to go. And so it got to the oil. Maybe I can just clean it up. Well, let's hope that it hasn't made it back to the center sump of the compressor. Let's hope that it didn't make it back up to the tippy top, which we haven't even talked about. This little teeny tiny hole is at the base of the orbital scroll in VRV3 compressors, and every VRV model compressor has it. It's just in a different spot. This little teeny tiny hole that you see is full of sludge, goes across the orbital scroll. Let me see, where's my orbital scroll at here? It goes across the orbital scroll to an oil pathway on the side. And that oil pathway is designed to lubricate the two plates that are put together to keep them lubricated. It keeps a nice little thin film of oil between the two scroll plates to ensure that they're lubricated properly. Well, the problem is that this tiny little thing is managed, the oil that flows through there between the scroll plates is managed by a screw. And so this screw is long enough with the threads at the size that they are to create enough pressure drop so that it doesn't blow the entire oil charge into the suction low side of the compressor, but it meters enough of the oil back to the actual compressor. Well, if these contaminants that you see on the right actually plug up this entire screw, this is called the thrust reduction screw. If it plugs the screw, then that's what's going to literally start your degradation. That's going to start this right here, the milling of your scroll plates. This is the start of that process. So even if your application is good and your charge is good and everything's good, but you didn't braze without nitrogen, a lot of that stuff is going to come up to that teeny tiny little hole here at the base of the orbital scroll, and it's going to plug that screw. I mean, that screw is, you saw it. It's super, super tiny. It looks like this. And once it plugs this screw, then now you're reliant upon the oil coming back down the suction line to keep that film between the two scroll plates. Start to lose a compression seal. You start to lose that lubricity that we're talking about. And that's when you start milling scroll plates. So how important is it to braze with nitrogen? It's extremely important.
It's the most important thing you can do during the install process.
Because the oil is going to clean those lines the longer it runs, and the more it flows through that system, and it's going to go to strainers, it's going to go to expansion valves, and it's going to go to this screw here. That's main job is to lubricate between the scroll plates. That's how important it is. Yep. And so that's the point. Because guess what? Cupric oxide, it doesn't stick to magnets. And so it doesn't care about these magnets at the base of the compressor. And so it's not going to it's not gonna end up in the safety catch that we have. It will end up in strainers. But it's that point where any level of contamination is bad. I'm not just saying that cupric oxide is the number one killer. I'm not here to say that. I'm here to say that any level of contamination is extremely bad for compressors. And
Right,
it's not
but
just VRF,
yeah, it's all compressors, any compressor.
any compressor. I'm here to advocate for all compressors. All
All
compressors.
compressors. Careful there.
I know. But here's that.
But to that point, right? Like if we have the cupric oxide, right? Like there's a strong chance that we're gonna have one of the other failure modes of, do we have metallic shavings now because the compressor wasn't lubricated? Probably. Do we have particles that are getting in top of and in through the scroll plate and rubbing and milling the surface like we saw like that? Probably. It all adds up, right? So let's, I'll say it here first. Do the job correctly so that we don't look at these pictures, right? These are horrible to see that all of this could have been prevented.
Yeah. And that's the thing. I had such a distaste for compressors when I started in this field because we lost a lot, right? They died pretty often, unfortunately. And it wasn't until I started tearing them down and doing the field research and then getting educated by some of the industry's best when it comes to compressor failure analysis and doing this on rinse and repeat, and understanding the science behind it and looking through oil analysis and spectrologists, all the things that you should do for science to understand this really well. Did I realize that compressors are actually built really freaking tough, and it takes a lot to kill the compressor. And come to find out, it's literally all preventable. To the point where they have in most VRV compressors, actually in all series, really, where they track the hours on the compressors and they're designed as a wear component, sure, but with a 20,000 hour lifespan, if not maybe up to 60,000 hours. I mean, I've got compressors that are still running on VRV2 at a church that have no issues, that have no failures because it was all done correctly. It was all done to the point where charge, line set, diameter, brazing with nitrogen, going through all the checks, ensuring that it was all done correctly to get the end result of this longevity of the compressor.
It's tough because like we joke around on like, oh, this place had 6 compressor failures and this one had 10 compressor failures. Like, well, why? There's a reason.
Yeah. Don't go and just change compressors. You need to investigate and understand the why. The why is the biggest part.
Right.
And again, here's my thing too. I'm going to implore you that, when we say the why, don't find one smoking gun and stop looking. If you find one, chances are there's probably 2, if not 3, if not 4, if not 5.
It harks back to one of our first episodes. Sorry, it goes back to one of our first episodes of like critically thinking about these failures and critically thinking about these systems. Is like, if the compressor failed, okay, why did it fail? Okay, well, we lost charge. Okay, well, why did we lose charge? Oh, it was vibrating itself to death and the cap tube broke. Okay, well, why was it vibrating? Yeah. Okay, well, what happened, right? So there's always a why. There's always more to think about on failures that potentially could save the customer another compressor in 6 months, 3 months, a year, 2 years, right? Like there's always another answer on what caused what. Now,
no, you keep going.
Maybe I should back up and say maybe I don't. Thinking in absolutes is not the right not the right frame of mind, but some failures do happen. They just happen, right? And those we can chalk up to manufacturing defect, right? Was one winding not as many turns as the other, right? Who knows? Unless you're cutting it apart and counting every one of those windings, you'll never know that. But I would venture a guess to say that 98% of compressor failures are preventable.
Yeah, and even if we, I mean, and that would be someone like, saying, hey, put a statistical number to it to justify all the costs associated with doing the cleanup kits, to doing the investigation, to measuring the piping line sets, to getting access to the entire lines, to doing all the things that are required. Trust me, I get how labor intensive it is. This isn't a 2-hour service call or a 2-hour repair. This is a couple of days, guys, to do this right. And if you just change out compressors and you're not seeing this, then, and that's fine, right? You don't have to I'm not sitting here saying you have to change out compressors and cut them open to get to the root cause. I do it because it's a lot of fun and it does help us get to the root cause faster. I'm saying that you need to go through and verify all the other things. We're talking line set lengths. We're talking piping diameters. We're talking a charge on the system. We're talking about sensors, expansion valves, maintenance items, maintenance points, ensuring that everything is copacetic, checking filters. When the system is running, did I check my strainers? Did I verify that I have good temperature drops, or not good temperature drops, good temperature drop on oil return, but not temperature drops on other strainers in the system, to where it is operating correctly? Have I done all those things, or have I just changed a compressor and walked away? Because if you have, you're going to be back.
Have you ever had to deal with warranty engine replacement on a vehicle you've owned?
I have never done that. No.
Okay. So one of the things that are required to validate warranty engine replacements is maintenance records, right? Like, do you maintain your system, right? And VRF manufacturers aren't requiring that, but I'm not saying it's a bad idea to require there to be written record of actual maintenance is being done to verify that system wasn't installed and then just left to run for a long time. Like, one of the things I've heard in the past, and I try to shut it down every time I do hear it, is, oh, these systems are supposed to be maintenance free. Right? And I'm not just saying filters, and filters is part of maintenance, right? But there's way more to these systems than just changing the filter, right? Like, all the manufacturers have some sort of service tool. Some of them have cloud tools now. Third-party manufacturers have cloud tools to give people access to these systems, so they're not have to be tied to the job site or tied physically to a condensing unit. All of this stuff is a good tool so that we don't get into these situations where we have 5 compressors on one condenser and then we're facing lawsuits and right, like, all of this matters.
Yep. No, and so to that point, also when we look at everything,
click back on that one. That was a good one.
This one here,
showing the terminal leads.
Yeah. So wait a minute, terminal leads inside VRF compressors are just uncoated pieces of metal. Yeah, actually they are. I don't know if you knew that or not. They're not coated in plastic or any of that. This is a Fusite terminal from the inside. I wish I should have got a freaking borescope to do it on this. Maybe I'll do that next time when I tear open a compressor next week. But so there's something to be said about electrical failures in compressors. Where does electrical failures take place in compressors? Right. And they happen right here on these terminals here. What happens? Well, let's paint a little picture for you. So all that paste you saw of cast iron millings down at the bottom, you notice that it's really small. And you can say, well, wait a minute. What if it sandblasts the windings? Well, first of all, there's no impellers or propellers or any kind of blades down in the rotor. It's literally just sleeve bearings and a very polished magnet with a low tolerance between the outside edge that's spinning at a high rate of speed. So there isn't anything to really like slosh the oil around or spin the oil in some kind of magical blender. So there isn't an environment where sandblasting is going to occur on these windings. Now, sure, could a screw or a large piece of metal get lodged in the middle of the rotor that's a magnet and spin around and hit the outside edge and nick one of the windings? Yes, I've actually seen it. Is it common? Not really, no. What's more common? Taking cast iron, coating these little spade connectors that you see where the compressors are connected, building up that metal paste to the point where it bridges a connection between the compressor connection terminal and the casing of the compressor to where it arcs out. And what happens when arcs happen, right? What happens when loose connections are present in electrical circuits? They draw a high current, amp draw. High amps means high heat. High heat means blowing out the actual pecker heads on these compressors. I mean, we've all seen it. It's that L8 that they keep power cycling, or L5, and then it goes to an E2, and the E2 they power cycle it twice, and what happens? It blows the terminal out of the compressor, and they lose the entire charge. And that's because of the metal shavings that built up on this terminal, because this terminal is horizontal, and it's right next to where the discharge line comes down. And so you got this piece of metal that's going to sit there like a little shelf, building up particles over time to where it bridges that connection. It grounds out. And thankfully, some compressors are a little bit better about sensing those grounds before they happen. So they don't, it's not a contactor driving these compressors. It's actually, an inverter board. It sees that voltage on the neutral line or the ground line, and it says, hey, ground fault detected. Don't run the compressor anymore. And it stops it from blowing out the terminals. But if you power cycle it enough, especially on a standard compressor, it will blow the terminals out because it doesn't know any better. And so, that's what happens inside of these compressors. That's what happens 9 times out of 10 when you have a grounded compressor that's failed. It's not due to winding degradation, because these windings are actually coated in a really thick, like epoxy, if you will. And I'd love to get
enamel.
the can. Oh, what's that?
Enamel.
Enamel. There we go. Yes. Sorry. Epoxy. Yeah. They just go to Home Depot and they get some epoxy and they just, slap it on there. That enamel wears out over time with temperature, sure. But you have to remember that the most compressors that have failed mechanically can also cause grounds and electrical shorts. It's not a failure of the windings themselves just wearing out to the point where they're touching each other. No, it's usually a mechanical failure of vibration, bearing wear, compressor seize that leads to overheat. Then the overheat leads to grounding over time. And so it's that cascading effect of, it wasn't struck by lightning. It was just poorly maintained to the point where it literally wore itself out inside to where it had nothing left to give and it just blew. And that's what happens, unfortunately. Anything you want to add to that?
No, I want to preface again, or I just want to say again, like, all of this stuff that we've talked about is preventable with just a little bit of extra work up front.
Yeah. And that's what it comes down to. It's not just, it's not just saying, hey, compressors, they wear out and then you change them, right? It's not a light bulb, right? It has so many hours and then you change it out. No, again, these compressors are supposed to last 15, 20 years. And if they're not making it to that point, then you need to stop and ask the question, what the heck happened? What does my screens look like? What does my suction superheat look like? What does my discharge superheat look like? What are my other signs? Did somebody lock this compressor out for 6 months and now it's full of, 68 ounces of additional oil that it's not supposed to have? I don't know if you saw that picture. You saw that picture I shared with you where the suction inlet on the compressor was literally so full of oil that it was dribbling out.
Yeah.
It was overflowing. It was locked out for an extended period of time. That's why we don't lock out VRF compressors for extended periods of time, because they will pool oil to the point where the compressor that's supposed to have the oil no longer
has it.
And then we get the unlubricated operation. Well, what happens after we get the unlubricated operation? It's this whole story that we showed you. It's the shavings, it's the magnets, it's the contamination, and that contamination goes through the entire system. It's sandblasting expansion valves. It's damaging and sticking, solenoid valves. It's subcooling valves that get stuck at 25% open or 15% open that flood the compressor at low load scenarios. Because that's where a lot of these failures come from is low load. You get to the point where only 2 fan coils out of 16 are calling for cooling, and let's say they're both 7K units. Well, that's a little bit over a 1-ton capacity, and it's a 20-ton system. And so it just sits there and it just very slowly limps along, real slow compressor speeds. And the subcooling valve doesn't see enough liquid flowing through the subcooled heat exchanger. And you get liquid flooding back to the suction line that washes the scroll plates at low load. And guess what? Oh, these units are actually in a server room. And so they never shut off. And so anytime there isn't an actual load on the building where other units are calling for cooling, it's washing the scroll plates with oil right off to the point where you get this milling down on the scroll plates themselves. So
yep.
It's a dirty business that we're in, but some of my favorite spots on the compressor where I love to look, since we're talking about it, we have my Dream Journal pictures pulled up here. Obviously, is the space of the compressor. It's the scroll plates themselves. It's the it's the sleeve bearing under the orbital scroll. It's usually, if it's dirty and it's slimy like this and it's plated, and there's discoloration or there's cracks, it's obviously overheat or a degradation of the oil to the point where the oil is just so thick that it sticks to everything. And then the last one that I love the most is it's the rotor. So the rotor is a giant neodyme magnet for Daikin compressors. And with it being a neodyme magnet, it likes to have this magnetic properties where things stick to it. And there is a little tiny, this is the bottom of it. This is a counterweight that's attached to it to kind of give it that, pull in the opposite direction. There's a little tiny plate that goes at the top of the rotor that shields the counterweight that's there from hot gas, from hitting the screws, from wearing it out, from discoloring it, from all the good things that wear and tear from hot gas. And when you pull that off with a few screws, anything you find underneath has been protected from the discharge gas. So there's nothing that will ever wash this away once it gets in here, because it's like a shield. It's bolted literally to the surface of the counterweight facing the opposite direction. And so it usually contains most of the contaminants you're going to find that were either floating in the surface of the oil or floating in the oil in general, once it floats into there, it doesn't float back out because there's nothing to wash it out. And so, and look, you can see on this one, I mean, the amount of copper shavings, or maybe someone blew a bunch of gold dust into it. It's most likely copper shavings, but it looks like a metal paste. And this is never coming out of there. And it's not because it's magnetic, it's because it's in a spot where, nothing can wash it away once it gets in there. It's like cracks and crevices between your shower tiles. You're just never going to get it out of there. It's just stuck forever. So it's kind of like a hidden spot on the rotor where if you really want to see how bad the contamination is, you pull this plate off the top of the rotor after you pull it out, and man, anything you find underneath is fair game. It's really revealing.
This was fair game.
Yeah, and here's another picture of that. Yeah, because again, these sleeve bearings, they're not cast iron. Most of these are actually a bronze copper mixture that's actually impregnated with PTFE. And that PTFE coating, Teflon, is designed to just help mitigate that wear properties of metal on metal. It's not really metal on metal. It's actually, it's that PTFE pushing against the other, coatings on the rotor itself and those bearings. So what happens when it gets super, super hot and breaks down? This is what happens. You actually get to see the bronze coating that's in there. You're not supposed to see this. This isn't supposed to be here. You've worn away the anti-wear coating on it to the point where you can see all those flakes and discoloration. It's funny because if you actually look up the patent, I say funny, it's funny to me. If you look up the patent for Copeland scrolls, you'll actually find where they show you the anti-wear surface on the scroll plates that they actually coated in Teflon. So yes, some scroll plates are actually coated in like a PTFE coating that protects them from that anti-wear to keep it from rubbing metal on metal, to keep it lubricated, keep it going in the right direction. So
I wonder if it's like similar to like automotive bearings where they use a material called Babbitt.
What's
Babbitt's like that's what like main bearings are made out of on cars, is a material called Babbitt.
Okay.
That's all it is a bearing material.
Okay. Yeah, I mean, and it might be. And I don't know the total secret recipe that most manufacturers for compressors use to, coat their wear parts. And when we say wear, the metal is supposed to grind on metal. It's usually coated, and then not only is it coated with an anti-wear coating, but also it has that oil. That oil keeps that barrier, right? It keeps them perfectly separated from each other. I don't know if you've ever cooked with cast iron skillet and you don't use oil. What happens? Gets pretty messy, right? Gets pretty sticky. You might as well just throw whatever you're cooking in the trash, unless it's scrambled eggs. And even then, it's a who's who. It's the same thing. These are cast iron. And so, polished, the purity is higher, obviously. But with that, these need oil. These plates need oil to maintain the surface tension, to maintain the temperature, to maintain the seal between the plates, to where we're not bypassing gas. Here's a great one too. You can actually see where some of the large shavings impacted on the wall of the scroll.
Into it.
Yeah, it just, again, when it comes back around to create that compression cycle, it literally just squished it right into the wall of the scroll. That's some damage.
I mean, the force inside that is crazy strong, right? Like,
it is.
And just think, right? Remember too, this is a VRF compressor, so it's not just 60 hertz, right? Like, it can go
168 hertz,
right? It can go twice that.
No, not even that. Yeah, it's like 254 hertz. I'm thinking RPS. I always compare it to it's like 7,800 RPM. You look at an angle grinder, and most angle grinders are like 5,000 RPM. I think like 3,500 RPM. It all depends on who you get. Walt has a variable speed one. You can turn the dial on it, and so we used to cut open some of the compressor connections on the outside of the legs and something to get it fit in the cutter. And again, it's fast. That's really fast. And when you just toss some metal in between there, grinding together, it's gonna just squish it, or it's gonna give way. And usually this results in scarring, and this is inefficient in the compression process too. That this is designed to have a nice oil seal. When it comes back to squish that refrigerant, right, to move it in the right direction, it's going like this. It's coming back together, and it's rotating and rotating and rotating. And in that rotation, when you get scarring like this, you give sections to allow bleed back, right? Yeah, pockets to where the pressure kind of pushes backwards instead of forwards, because it can bleed back through the scroll coverings. Now, I don't know if there's any statistical or scientific studies done on metal contamination and lower COP or something like that, but for this,
Well,
it's not good.
I'd be really interested to see, like, when we get a lock rotor code, right, like a L5, what the rotor actually looks like inside there. If it does have all those galling and pockets on there, if the lock rotor comes from, if it's stuck, I get that, right? If it gets stuck, but if it had all those pockets in there and then all of a sudden, just like you said, the refrigerant can't flow in the direction it needs to, and you get a little bit of like pressure drop or excess pressure that the scroll can't handle, and it just locks at that.
It does. So I had a compressor where we tore it apart, and it was a seized compressor, VRF. I believe it was vapor injected, if I'm not mistaken. And when we got it apart, we couldn't get the rotor out. Two guys prying on it with a pry bar. We ended up having to cut the top back in a couple sections and kind of peel it back like an onion, and then hit the top with a sledgehammer. And even then, she didn't want to give way. And we finally got it out, and come to find out, the upper sleeve bearing got so not worn out, but it got so hot being unlubricated that it actually fused to the bearing housing, where it was like you said, it's like a vapor lock, right? It's like a mason jar that has hot liquids
Right.
put in and it cools. Like, you can't get that lid off. It's the same thing. Like this compressor literally seized on that to where you couldn't even rotate it. And we eventually beat the snot out of it and got it out, but it was just wild to see that, like, it's not getting locked at the scroll, it's getting locked at the rotor, either at the lower or the upper bearings, to where it can't rotate anymore. Now, I have seen where the scroll won't rotate anymore because it gets scroll wall pieces in it because it broke apart.
Right.
The orbital scroll broke apart because of liquid refrigerant coming back. But with that, it's one of those things that, that happens, sure, but it's usually the rotor itself, the bearings wearing down, overheating, and then fusing to some part of the actual bearing housings where it literally physically can't rotate anymore. It's melted to it, as if you want to, welded to it if you could.
Welded, yeah.
Yeah, and so, because let's be honest, what is galling? Galling is the circles that you see here on the surface. It's all this material that has been broken down around the edges. Look how rough and jagged these are around the edges. Galling is where metal gets so hot on the surface that it literally fuses to the other piece of metal and then breaks apart instantaneously. So it's a fuse break like that. Boom, boom. And it's that on repeat over and over and over again because of unlubricated operation. And the rest of the scroll stays somewhat fairly cool because it's not coming into contact with the surface like the tops of these scrolls are and the bottoms of these scrolls. And so, it doesn't get it hot enough to melt it all the way where it would break off or brittle or shatter. It's just enough to wear the surface like this to the point where, it breaks off. And then I would compare this to a brake pad in a car, right?
Yeah.
Where you wear it down to the point, because that's what that is, right? That's literally pushing up against. And I don't know, what was brake pads made of? I don't even know what the material is there. I feel like
ceramics or organic materials.
Yeah, and so that's designed to stop the wheel, right? It's designed to stop the car going no matter what speed it is on a rotor, and the rotor, is similar to this on that car, and it to the point where if you run out of brake pad, what happens? It's metal on metal, and you start to scar the actual rotor. Am I saying any of that correctly?
Yep.
Not being from the automotive world.
Nope.
Yeah, and so it's just the same application here. You run unlubricated, it's like driving your car with worn out brake pads. You're just not going to stop. Not without tearing something up and getting really, really, really hot. It's those videos you see on YouTube or on Facebook or Instagram where the guy's driving the car down the highway and like the tire is on fire.
Orange. Yeah.
Imagine that, but like inside of your actual scroll compressor.
Like going, 10 times faster.
But that's what's happening in these scroll compressors, and it is preventable. You get a customer, you get a client that you've never seen before, you get a system that's new to you. There's a lot of things that you can do. There's a lot of things that you can go through that you need to work through to find out what is the root cause. Obviously, getting your client air conditioning is probably at the top of that list because they're screaming, they're yelling, they want to get this unit running. Weigh your pros and cons, weigh those options to your client, your customer, but just know this is it, right? This is what's happened. This is what could have happened. There are steps that you still need to do to get to the root cause of this.
Yeah, set the baseline.
Yeah, and it's that offer and decline. If they decline it, then you'll be back in 2 months to change a compressor in a year. I've seen it 6 hours. It's all just dependent upon how bad it actually is.
Yeah,
So,
if you need some pointers on how to approach those conversations with the end users and customers, like, feel free to reach out. Like, uh, I'll give you some options, right? But setting the baseline and setting the expectation of the customers, like, yes, you had a failure, and yes, we know you want to get it online, but there is going to be something that caused that failure, and you know, here's our price to determine that. If you deny it, then we understand, and we'll do what you need to do to get cooling back. But you
here's the
know,
risk.
right,
What are the things
here's
worth
your
it?
risk.
Yeah. Yeah, and is it worth the risk? I don't know, you tell me. Do you wanna pay $10,000 again to change this compressor out?
Right?
I
You
mean,
want
probably not.
to probably not, but you will.
Well, and these are things that are measurable. Suction superheat. If I turn the system back on after changing out a compressor and I'm measuring suction superheat, discharge superheat, maybe system subcooling, looking at the system operation, checking for oil return on the suction line, checking the oil return on the system, we're checking all these things together. I know that, and we ran through this unfortunately one time. Learning curve here, where you turn a system back on because they got to get it on. They have a compressor in house already ready to go. You change it out same day, and you turn the system back on, and it's got a 1 degree suction superheat. How long do you think that compressor is going to last? It's not going to last very long. It may make it like 6 hours. It might make it 24 hours. It all depends on how hot the building is and how much they run that system. It's just one of those things. If you leave it, it's going to fail.
Right,
It's not a matter of and if or but. It's going to fail. And so it's that conversation that you have. Hey, it's 10 p.m. I got it running, but we can't find the bleed back inside the building, and you got one suction superheat. I wouldn't leave this running. If you want to leave it running, you're going to lose this compressor or another one in the system. That offer and decline. Okay, we'll leave it running then, and you suffer the consequences, unfortunately. And I mean, they could still get mad at you, I guess, but it all just depends. So
it's how you feel at the end of the day.
I
You
do,
did the right thing per the customer, so
and that's it, right? That's that whole offer and decline. So that is the in-depth analysis of compressors, what internal components that they have when it comes to VRF compressors, high pressure shell compressors in VRF systems, and the mitigating factors that all contribute to failures. And it's that whole chicken and egg. Which one happened first? Who really cares? Go do all the other things we talked about: measuring piping, diameter, charge, cleanup. You do those things. Who cares what killed it first? You found that it's contaminated. You found that there's a problem.
right,
Move on. It
fix it.
doesn't really, yeah, it doesn't really matter, because you can sit here and speculate, well, are you saying I need to change out all my piping? Are you saying I need to change out all my expansion valves? No, let's do the other things first that we can measure and we can do first, and then run the system and evaluate how it's performing and what
Right.
things might be addressed. So
All right. Well, Roman, thank you for your time again, and thank you everybody for listening.
always a blast, man. Until the next time.
Until next time. See ya.